Hi, my name is Shaoyue and I'm currently a master's student at New York University. Today, I would like to introduce AdaptiveVoice, an optimization approach that automatically adapts voice messages to the current user's cognitive load. This work is in collaboration with Songming, Jialin, Wang, Hai-Ning, Liang, Xuhai, and Yukang. Voice systems have become popular and valuable for drivers driving through complex and unfamiliar road networks. Current systems play voice messages in a predefined manner with fixed content and at a fixed speed. However, as driver may encounter different events while driving, which can induce different levels of cognitive load. They may have diverse capabilities and capacities of consuming the information from voice systems and following their instructions. As a result, the same message can be overwhelming to a driver with a heavy cognitive load, while more details can be appreciated when the car is at a stop. So the question for our research is how can we automatically adapt voice messages to provide sufficient but not overwhelming information to assist their driving? To address this issue, we propose AdaptiveVoice. AdaptiveVoice automatically adapts voice messages based on users' current cognitive load. Our optimization-based systems adapts levels of detail, repetition, and speech speed, thereby optimizing user experience and comprehension.
Exit the overpass in 200 meters and go straight on Great Western Road. Straight.
Looking at the evolution of voice user interface, or VUIs, we observe their increasing integration across various sectors, from smart homes to driver assistance and even accessibility enhancements. For individual user, the interaction requirements with voice user interface can vary depending on the context in which they are used. In driving scenarios, previous work has explored various formats to deliver the messages or encoding richer information via spatial auditory displays. Instead of changing the sound effects, what we want to do is to optimize the voice messages for users' current mental state while keeping the core information the same. As a starting point, we select the user's cognitive load as a factor to adapt VUIs to. Let me explain what we did and how we did it. Based on the user's current cognitive load, we want to automatically decide on the levels of detail, repetition, and speech speed. The level of detail represents the amount of information delivered by the voice messages. Here you can see an example with 5 levels of detail, varying from the lowest level of only the direction information, for example, the right, to the highest level of fully detailed instructions, such as turn right at James Street in 100 meters and switch to the red lane afterwards. For repetition, it's pretty straightforward. We want to decide whether the message should be displayed twice. Thirdly, voice speed. Our approach decides at which speed, slow, medium, or fast, the voice messages should be played. The question now becomes how do we determine adapt rules based on the current cognitive load? To begin with, we conduct the first user study, data collection. We aim to collect both objective and subject data from users to understand users' preference and behaviors for different formats of the voice message on their varying levels of cognitive load, and conclude the adapt requirements. We apply a dual-task experimental design method. The study contained 2 sessions. In the first driving simulation session, the primary task is to follow the voice instructions, and participants need to select an operation to take for a driving task based on the information they interpreted from the instructions. The secondary task is designed to alter participants' cognitive load by changing the task difficulty. Participants are required to memorize a set of numbers and determine whether the current stimulus is identical to a previous one. In the second reflection session, the secondary task is the same as the first session. The primary task is to ask participants to revisit all the message formats and select the best format for each level of cognitive load when they perceive it. Objective results from the first driving simulation session show that the presentation of voice messages, especially the levels of detail, significantly affects users' task completion time and accuracy. Based on the study result, we identified the 4 requirements for optimizing voice messaging system in real time. The first is cognitive load sensitive information requirement. The system should adapt the level of detail in the message according to the user's current cognitive load. For instance, when cognitive load is low, the system could offer more elaborate messages. Conversely, when the cognitive load is high, the system should prioritize simplicity and clarity. The second is context-aware repetition. Repetition should be employed as a feature that can be turned on or off based on the cognitive load and the importance of the message. The third is speech speed modulation. The last but not least is consistency with the prior user interactions. The system should maintain consistency in the presentation format based on prior user interactions and preference. For example, if a user commonly prefers instructions without repetition, the system should adhere to this format. We use HP Robot G2 headset to estimate the real-time cognitive load. As reported, it provides a robust cognitive load estimation based on behavior and psychological measurements. In an experiment with 738 participants, it achieved an average classification accuracy near 80% with a mean absolute near 0.1. Based on the 4 requirements, we implement an optimization-based algorithm to adjust the format of the voice messages sent to the users in real time. For the inputs, we set the user's cognitive load and their interaction history as real-time inputs while the model is running. To encode the requirements into our model, we define 3 sub-objectives according to the 3 requirements: the utility of level detail, repetition, and speech speed. Our optimization aims to maximize the overall weighted sum of the objective function. For the consistency requirements, we use this format to calculate the probability of the level occurrence. The more the level appears, the greater the probability it will appear later. We also have 2 constraints to limit the range of potential solutions. First is the cognitive load constraint. We assume that cognitive cost caused by all exhibited speech parts cannot exceed the total cognitive capacity when combined with the user's excess cognitive load and should also leave a minimum remaining capacity. Second is the level presentation constraints. We should avoid duplicate levels and trivial solutions that appear at the same time. The formula ensures that each element is shown at a single level. To evaluate the performance of the AdaptiveVoice, we simulated a driving task in a city-sized virtual environment. We conduct the experiment in virtual reality to gain complete control of the overall environment while keeping participants safe. Based on previously, we designed driving scenarios that could induce different levels of cognitive load. We changed the intersection types such as straight road and crossroads. Also, the level of information and chooses 3 special cases containing incidents. As a heads-up display showing visual guidance is commonly considered effective in driving assistance, we compare the proposed method with a fixed format baseline in the conditions of, with, and without visual guidance on the heads-up display. Objective results indicate that users benefit from AdaptiveVoice with reduced response time and improved driving performance, particularly when their driving is augmented with heads-up displays. The subjective results collected from the questionnaire and semi-structured interview indicated that AdaptiveVoice can improve efficiency and user engagement. It can also enhance the driving experience by aligning with the driver's need for dynamic, real-time information, thereby fostering a greater sense of security and reliability compared to the fixed format. AdaptiveVoice with HEDs is the most preferred condition by users. We expect AdaptiveVoice to be beneficial for a broader range of applications beyond the driving assistant, as long as the user's cognitive load dynamically changes. For instance, when the user is situated in a relaxed state near the window, the cognitive load can be at a low level if the user inquires about evening restaurant recommendations and their signature dishes. The smart home system can offer a comprehensive list.
Hello, can you recommend me some restaurants and what are their special dishes?
Sure. Here are some options. La Bella Italia, it's known for their authentic pasta and pizzas. Their special dish is fettuccine alfredo. Sakura Sushi, famous for fresh sashimi and a variety of sushi rolls. Dragon Roll is delicious.
In contrast, when the user is engaged with work tasks in the study room and the cognitive load level rises to a high level, a more concise response is appropriate. For instance, if a user inquires about the necessity of carrying an umbrella the next day.
Hey, do I need an umbrella tomorrow?
No, you don't.
Now, let's move on to the limitations and future work. More adaptive features, including volume, tone, and frequency of the voice instructions, can be adjusted in the optimization, and factors including the user's driving skills, traffic situations, can also influence optimal manner of presenting voice instructions. As a starting point, our current adapt method follows a one-size-fits-all approach that looks for common behaviors among all users to balance performance and simplicity. We believe that it is an important future direction to explore personalization of AdaptiveVoice, taking users' driving skills and experience together with their cognitive capacity into consideration. Currently, we use HP Reveal G2 headset for real-time cognitive load estimation. However, we recognize the potential in exploring simpler behavior-based methods for estimating cognitive load, such as analyzing steer wheel angle as a proxy. Now, to wrap up, we contributed an optimization-based voice assistant technique that automatically adapts level of detail, repetition, and speed of voice instructions to assist users when they have various cognitive loads while driving. Please see our paper for details. Thanks for listening.